Final lesson of the course is this one on the intersection of three planes, which is quite a complicated topic. Tomorrow, or it may not be tomorrow, but I think I will release the this last one here, the supplement. You could, it's not required, but it might be useful, and it certainly makes what we're doing today a little easier, I think, at least organizing your work. So three planes can intersect in 8 different ways, and a lot of today is about trying to come up with a scheme or a plan for how to organize these 8 different things. Because, if I asked you to hold 3 pieces of paper, all the different ways you could hold 3 pieces of paper, this is what you would come up with eventually. I mean, these are all the possibilities of how you could do it. You could have all 3 pieces of paper parallel and none of them touching. You could have all 3 of them parallel, 2 of them touching and 1 of them not. Or you could have all of them parallel and all of them touching. So the first, way to sort of sort today is to analyze the normals and whether they are parallel. If all 3 of them are parallel, then you're really only contending with these 3 options, and these 3 options are not that difficult to tell apart. You try to intersect plane 1 with plane 2, see what you get, and then try to intersect plane 2 with plane 3 and see what you get. If 1 intersects with 2 but not with 3, you have that. If 1, 2, and 3 all intersect each other, you have that. If 1 doesn't go with 2, and 2 doesn't go with 3, and 3 doesn't go with 1, then you have that, right? So, I'll show you how, of course, how you can sort of mathematically distinguish them. But the first way you should think about this is, okay, if all 3 are parallel, it's cut my possibilities down from 8 to just 3, and then all I need to do is see, is it consistent, is it inconsistent, or is it inconsistent and all of them are inconsistent, right, with each other. Now, if it's the case that 2 of the normals are parallel, so you're holding your pages in such a way that 2 of them are parallel and 1 of them is not, then there's only 2 different ways that could go. Either the 2 planes that you're holding are distinct, and therefore the third plane cuts through both of them, but of course there would be no intersection here, because remember, an intersection would be a point that's on all 3 pieces of paper. Since paper 1 and paper 2 share nothing in common, no intersection is possible. On the other hand, if paper 1 and paper 2 are actually on top of one another, then the third one must intersect it somewhere. Just think about yesterday's lesson. I mean, this is just the same question as yesterday. When you have 2 planes and that are not collinear or not parallel, because you have these 2, pi 1 and pi 2, are really just the same thing. Now, where it gets more interesting is if none of the normals are parallel. Now, if none of the normals are parallel, there are 3 different possibilities. There is what we call intersecting in pairs, where it's kind of like it creates a triangular. There's like a triangular prism in between the 3 planes, and the 3 planes intersect one another in lines, but none of those lines are actually common. And remember, in order for a system to have an intersection, all 3 things must meet in the same place. In this case, that is not true. Secondly, you could imagine 3 planes meeting like at the spine of a book, like all the different pieces of paper, and the spine of the book is where all the pages meet, and then they all kind of fold out from there. So 3 planes can meet in a straight line. Finally, 3 planes, if you consider, let's say, the wall with the door, the front board of the classroom, and the floor, they would all meet in one place, which is the corner, right? The front corner of the room. So these 3 are the most difficult, but let's consider 0 solutions, infinite solutions, 1 solution, 1 point only. Now, telling these 3 apart mathematically, Again, you can cut them down a little bit. So all three of them have something in common. None of the normals are parallel. Now these normals, the normals on these two, despite the fact that they are not parallel, they are still coplanar. So all the normals still lie on the same plane. If you can see that, then you know it has to be one of these two. If the normals do not lie on the same plane, you have to have this one. Right? So remember, our test, there's a test to see whether normals are coplanar. Normals are coplanar if, right, n1, n2, n3, okay, if the, obviously, yeah, so if n1 dot n2 cross n3 is 0, they are coplanar. So in this situation and in this situation, you could tell that they would not intersect in a point, for example, if you knew that the normals were coplanar. So if all three normals are not parallel, but nevertheless they are coplanar, you have to have one of these two. If they're all not parallel and they're not coplanar, you have to have this one. Okay, so how do you solve these things? Ultimately, what you are trying to do is you are trying to look at these three equations and reduce it down to some solution. So your ultimate goal is to eliminate variables and solve for x, y, and z. That's what you're ultimately trying to do. And you already know how to do this, you just may not have done it with 3 before. So let's write down what we know. 2x plus y plus 6z equals 7. And then let's take the next equation, 3x plus 4y plus 3z equals negative 8. So let's say step 1. Use the first two equations to eliminate a variable. So in this case, I think it would be easiest to eliminate z. Let's just say. So what do I do to eliminate z? I'm going to take equation 1, and then I'm going to double equation 2. So 6x plus 8y plus 6z equals negative 16. Right? I'm allowed to do that because this equation and this equation are in fact the same. They've just been, everything's been multiplied by 2, but it would still create the same plane. Then I'm going to subtract, and I get 2 take away 6 is negative 4x, y take away 8y is negative 7y, 7 take away negative 16 is 23. Okay, so I've created a new equation. Step 2. Use two other equations, 1 and 3, or 2 and 3, to eliminate the same variable. Okay, so I want to eliminate z. So I think 2 and 3 would be kind of tricky because they don't line up as nice. I guess it doesn't really matter. Sure, let's use 2 and 3, whatever. Okay, so let's go down here. We're going to write equation 2. 3x plus 4y plus 3z equals negative 8. We're going to write equation 3. X minus 2y minus 4z equals 9. Now we need to get the z's to be the same coefficient, so we're going to multiply equation 1 by 4 and equation 2 by 3. Okay, so in the first case, 12x plus 16y plus 12z equals negative 32. So same equation, I just quadrupled it. Second equation, I'm going to triple. Okay, so I tripled the equation number 2. Now I see they both have 12z, so I'm going to add them together. 15x plus 10y is equal to negative 5. Okay. Step 3. take the two equations with the missing variable and eliminate another variable. So I created this one, which I'll put in blue, and this one, which I'll put in orange. So copy orange, copy blue. Okay, now these two, again, they have an X and they have a Y. There's no Z, so let's use them to eliminate again. So what I'm going to do, it's not particularly easy to work with either of them, so let's say multiply the top one by 15 and the bottom one by 4. Okay, the top one times 15. Negative 60x minus 105y is equal to 345. The bottom one by 4. 60x plus 40y is equal to negative 20. Okay, now I'm going to add. I get negative 65y is equal to 325, and so y is equal to negative 5. Okay. Now, if y is equal to negative 5, use your solution to backfill previous equations and solve for the other variables. So let's go back to my blue equation. Okay, I know that y is equal to negative 5, so I go negative 4x, take away 7 times negative 5 is equal to 23. Okay, negative 4x plus 35 equals 23. Negative 4x equals negative 12. X equals 3. Okay, and then we'll do the same thing with z. So we'll just go back up to whichever equation. Doesn't matter, you could pick any of them. So go back to this one. We'll go 3 times 3 plus 4 times negative 5 plus 3 times z equals negative 8. So 9, take away 20 plus 3z equals negative 8. 20 goes over to the other side to make 12. 9 goes over to the other side to make 3, so 3z equals 3, so z equals 1. So therefore, the three planes intersect at a single point, and that point was 3, negative 5, 1. If we go back and take 3, negative 5, 1, it should work in all three of these equations. Again, let's use the benefit of technology to help us check our work. Okay, so I'm going to type the equation for the planes. So 2x plus y plus 6z equals 7. 3x plus 4y plus 3z equals negative 8. X minus 2y minus 4z equals 9. Then I'm going to go, let's take a look at what they look like. Okay, now again, this can be a bit difficult to interpret, so let's drop the plane. And you can see that none of those are parallel, and none of them are coplanar. So, the three of the three normals are not coplanar. And when we zoom out, we notice that there's a specific spot right in this corner. And again, it can be a bit difficult to see this. Maybe what would make this a little bit easier if we... Okay, so again, blue meets green meets red at one specific spot, right? This little, like, sort of corner, so to speak, right there. Now we've done some math to suggest that the place they meet is 3, negative 5, 1. And you'll see that that point perfectly matches that corner where they all meet. Again, an easy way to check your work here, you can type distance A EQ1. It's 0 because A is on that plane. Distance A EQ2, it's 0, and distance A EQ3, they're all 0. You can also say intersect EQ1. I don't think you can do all three at a time. So what you would do is you'd intersect plane 1 and plane 2, then you'd intersect plane 2 and plane 3, and then you'd intersect those two lines. And that's another way you could get to 3, negative 5, 1. Okay, so if you intersect the two planes separately, get their two lines, and then find where those two lines cross, that's another way that you can get that answer. Okay, so this is good. Now, again, I told you that you could only get this system if the normals are not parallel and they're not coplanar. So they're certainly not parallel because you have 2, 1, 6 and then 3, 4, 3. There's no way to make those parallel. But let's just show that they're not coplanar either. So n1 is 2, 1, 6, n2 is 3, 4, 3, n3 is 1, negative 2, negative 4. Okay, and then let's do the coplanar test. Okay, the coplanar test is dot n1 with cross n2, n3. Okay, and you see that their triple scalar product is not 0, and therefore they do not lie on the same plane, which you can kind of see from looking at it as well. Okay, so they're not coplanar. If they're not coplanar, they must meet in exactly one point. Okay? All right. So that's good. So it turns out that these are probably easiest when they meet in one point. That it looks like the trickiest situation, but it's probably actually the easiest to deal with because you use this method of double eliminating, and then eliminating again, and then you don't get your other variables. Let's try another one here. So again, you can just start by trying to eliminate right off the bat. You don't have to do that coplanar test, although I think I will just to demonstrate again. So let's look at this one. The first normal is 1, negative 5, 2. The second normal is 1, 7, negative 2, and the third normal is 8, 5, 1. Now, it's pretty obvious that none of those are parallel. However, they may actually lie on the same plane. Right? You can imagine a plane that might contain all three of those if it comes right out at us from here. Let's do the coplanar test to check. So I'm going to do n2, so cross n2 with n3, and then I'm going to dot that number or that vector u with n1. Now this time you can see that the triple scalar product is 0 because in fact all three of these lie on the same plane. Right? And so if we were to say, let's say we were to go O, and then we were to do a plane defined by O, N1, and N2, right? You can see that N3 is also on that same plane. So when the normals are coplanar, okay, that eliminates the possibility that these are going to meet in one single spot. So I kind of know what I'm looking for here. Let's just write down what I know. Okay, so let's start. The normals are not parallel. And you can easily see that 1, negative 5, 2 is not equal to k times 1, 7, negative 2. There's just no way that, they both have a 1. So how do you make the 5 into a 7 without changing the 1? You can't do it. So their normals are not parallel. Okay, the normals are coplanar. And again, I found that out because I'm just going to copy paste this because this is irritating to type. Okay, I crossed N2 with N3, and I determined that that cross product dotted with the other normal gave me 0. So what this means is I therefore have either case 6, which is intersect in pairs and inconsistent, like there's no answer to that one, or I have case 7, which is they all intersect in a line. Again, just for the sake of training, I know you're not used to these yet, you don't recognize them, so let's just copy paste these and bring them down here so just so I can discuss this a little bit further. So I know I'm expecting one of these two as my answer at this point. So either they do in fact intersect, and they intersect in a straight line with infinite solutions, or they don't intersect all at the same point. So this is case 6 here. This is case 7. Okay. So how do I tell the difference between these two? So to tell the difference, there's a couple of things you could do, of course. You have to try to solve the system. So I'm going to suggest, again, this is not the only way to do this, but I'm going to suggest that what we do is the same thing we did for A. All right, so we're going to try and go through this elimination thing and see how it would work differently if you're in a different scenario. Okay, so let's do the same thing. So we'll start with the first two equations. X minus 5y plus 2z equals 10. And x plus 7y minus 2z is negative 6. Okay, I'm just going to double check that I wrote those down right because, yep, I didn't. It's one of those things where if you don't, any mistake cascades into a lot of wasted work, so it's good to check. Okay, these, I don't need to do anything special here. I can just add the systems to eliminate z. I could also subtract to eliminate x. I mean, it doesn't matter. Let's add them together. X plus x is 2x. Negative 5y plus 7y is 2y. And then you get 10 plus negative 6 is 4. Okay. Then what we're going to do, let's say here, so we're going to work with equation 1 and equation 2. Let's say, so since we're eliminating z, if I look here, it really doesn't matter. I mean, it would be easy to eliminate with 2 and 3, or with 1 and 2. So let's just use, let's work with 2 and 3. Oops, equation 2 and equation 3. Okay, so equation 2, x plus 7y minus 2z equals negative 6. Equation 3, 8x, 5y, z, 20. Okay, 8x and everything's positive, yeah? Okay, so again, if I eliminate z, I want to double equation 3. So I get x plus 7y minus 2z equals negative 6, and underneath that I get 16x plus 10y plus 2z equals 40. If I add them together, I'm going to get 17x plus 17y is equal to 34. Now, this is going to cause us a bit of an issue because, so let's call this the orange equation, and we'll call this the blue equation. Now, once again, we got to use the results to eliminate another variable. Okay, so let's take our orange equation, which is right here, and our blue equation, which is right here. And now what we're going to do is we're going to, simplify them. So what I'm going to do is I'm going to divide. You can multiply if you want, but I actually noticed that these can be divide the first one by 2, divide the second one by 17. Okay. What happens? I get x plus y equals 2, and then x plus y equals 2. Now when you try to eliminate this by subtracting, you get 0 plus 0 equals 0, which is always true. Okay, now what does that mean? 0 plus 0 equals 0 is always true. Well, since it's true, you must have a solution. Okay? i.e., it has a solution. Okay? That means this is out. It has to be this one, because we got a statement at the end that is true. Now, how do they actually intersect, though? We have not discovered that. So, again, what do you do when you get down to this? You're in case 7, and you get down to this 0 plus 0 equals 0 thing. What are you supposed to do next? So to create the line, okay, go back to your last known equation and substitute a parameter t, like what we were doing yesterday. Okay, so we had x plus y equals 2. Let's let y equal t. Doesn't matter which one, that would be equally difficult to use, so or easy. Let y equal t. Therefore, x plus t equals 2, and x equals 2 minus t. Now let's go back to another equation involving z. Doesn't matter which one, we'll just take this one. And we'll say x is 2 minus t, so 2 minus t plus 7t. Take away 2z equals negative 6. We'll isolate everything onto one side. Let's bring the 2z to the other side and the 6 to our side. So 2 minus t plus 7t plus 6 equals 2z. Therefore, you have 8 plus 6t equals 2z. Therefore, 4 plus 3t equals z. So the line of intersection that we have, x is 2, y is 0, z is 4. And the direction vector, x was negative 1, y was positive 1, z was 3, where t is some number in the real numbers. Now, to check that this is right, 2, 0, 4 must be on all three planes, and also 2, 0, 4 plus negative 1, 1, 3 must be on all three planes, right? So it's like, it would be like saying this point has to be common to all three. And also, if I were to move a direction vector, of course I could also subtract a direction vector or multiply any fraction times that direction vector, must also be on the plane. So we could check that. I don't think it would be too hard to check 2, 0, 4. Let's just go back. Let's sub in 2, 0, 4. So 2 for x, 0 for y, 4 for z makes 10. Yes. 2 for x, 4 for z is 2 take away 8, which is negative 6. Yes. 2 for x makes 16 plus 4 is 20. So that point is in fact on all of them. So that's good, right? That means we must have done this right. We should also be able to check the point, you know, also you could check, let's put, you know, plus k. So, you know, like if let's say for example I made k 2, then when I did 2, 0, 4 plus, now if I make k 2, this would be negative 2, 2, 6, which would be 0, 2, and 10. So 0, 2, 10 should also be on all three of them, right? So if y is 2, then you have negative 10 plus 20 is 10. That's good. If y is 2, you have 14. Take away 20 is negative 6. That's good. If y is 2, you have 10 plus 10 is 20. That's good. So I know I've got this right. They intersect in a line, and I have found the correct line. Again, if you're not doing it by hand, we can benefit from using the technology that we have. So I could use these normals, I guess, but let's just hide the normals and hide this plane. Start over. Okay, so let's type out the equation. So x minus 5y plus 2z equals 10. X plus 7y minus 2z equals negative 6. 8x plus 5y plus z equals 20. And then if I go intersect, okay, intersect EQ1 with EQ2, okay, it creates a line. And then I go intersect EQ2 with EQ3, it creates a line. And if I intersect those lines, intersect FG, yeah, okay, it doesn't know what to do. So we finally outsmarted GeoGebra. I have to look at the picture, I guess. When I look at the picture, I notice that all three planes are kind of like the spine of a book, where the pages are coming out from that spine, right? Like all three of them. You can imagine kind of looking at it like straight down, and you can kind of see all three of them like a top, right? And so they intersect in a line, right? And that's the line that it is. Now again, GeoGebra, it picks points in a kind of unusual way. So what we might want to do is type in our line. So we're going to go P equals, the point we found was 204. And the direction vector we found was, let's call it M1, is negative 1, 1, 3. So if I go line P M1, that's the line that we came up with. Of course, it does look right, but you can check by going distance between H and F, and it will come up with 0 because they are in fact the same line, right? I mean, I guess you should be a bit careful with that because if they intersect, I think it would do the same thing. But based on the picture, you can observe that, yeah, that line is good. Okay, so again, if I hide the lines GeoGebra made and just keep my line's perfect, right? Okay, so that's how you could solve case. This is an example of a case 7 question. Okay, so maybe let's just write that down. This is a case 7, which we didn't know until we solved it. I guess I'll put it down here. So case 7, intersect in a line, and that line is what we discovered right here. Okay, now I don't want to do this one. Do they have the reason I'm hesitating is because this one I can see is parallel. When they're parallel, it's much easier. Like it's when they're not parallel that this is most difficult, and I kind of want to do one that intersects in pairs before we do a parallel one. What have we got here? We only got 3 left. Well, whatever. We'll just do them in the order, and if it doesn't come up, I'll just make up another one. Okay. So, what were we supposed to do here? Describe the number of solutions and how the planes intersect. So, you know, for this we didn't actually... Oh, well, I guess it doesn't matter. Okay, these 3 planes intersect at a single point, and that is case 8. Okay? This one, they intersect in a line. That's case 7. And just technically, there's infinite solutions, right? Because a line has infinite points. There'd be infinite solutions. Okay, determine the solution to the following set of planes. So, first step when you're looking at these planes is to compare the normals. Now, I can see that N1 is equal to K N2. Not N2, sorry, N3. Right? Because N1 is 3, 1, negative 2, and that is equal to K 12, 4, negative 8. In this case, the K would be 1/4, right? If you take 1/4 of N3, you would create N1. So that means, this means 2 of the planes are parallel and 1 is not. So let's look back at our cases. What might this mean? When 2 planes are parallel, you have these 2 choices only. So it has to be case 4, which will give us no solutions, or case 5, which will give us a solution in a straight line. Although, it should be noted that all I really need to do to tell these 2 apart would be to check if the 2 parallel planes are in fact the same or if they're distinct. Because if they're distinct, then I can do this and I'm immediately done with the question, right? Alright, so where are we? I'm going to just move this to the other page. There's no way we're going to have that much room. Okay, so let's compare pi 1 with pi 3. Okay, so how would we, if you were to quadruple the first one, so let's say we were trying to solve it. So 3x plus y minus 2z equals 12. 12x plus 4y minus 8z equals negative 4. We're going to multiply EQ1, the top equation, by 4. We get 12x plus 4y minus 8z equals 48. Underneath it, 12x plus 4y minus 8z equals negative 4. Obviously, when you subtract these equations, you're going to get 0 equals 52, and that statement is false. Therefore, there is no intersection. This means we must be dealing with case 4. Okay, therefore we're dealing with case 4. Okay, which is two planes are parallel and distinct. And the third plane intersects them at different places. Okay, so what we do is we say there's no solutions. Okay, not much else to do with this one really. You can see that when I tried to solve it, I came up with an absurdity, right, or a false statement, 0 equals 52, which means there's just no way to make these equations work. Because I already analyzed the normals, I knew which possibilities I might have to be dealing with. I should write that down somewhere. So just, sorry, right here. We are dealing with either case 4, inconsistent, or case 5, consistent. Okay, so the one of those two, it had to come up. So we're coming up with case 4. Okay, so this is case 4, and there's no intersection there. Okay, let's draw it again to confirm our mathematics. Okay, so 3x plus y minus 2z equals 12. X minus 5y plus z equals 8. 12x plus 4y minus 8z equals negative 4. And again, I think this was probably easier when we used colors, so let's... Okay, so you see blue and red will never cross. Green crosses each of them, but in different spots. And so what you're looking at there is an example of case number 4. Two planes are parallel, but those two planes are distinct, and therefore you do not have any intersection. So what we did was right. So let's copy paste the pictures just because I really want you to reinforce. Sorry, it's a bit tedious, but okay, so there's case 4 and 5 with the two that we were trying to tell apart. Okay, another one. Looking at the normals, this one has a 1 on the x. This one has a 2 on the x. This has a 3 on the y and a 1 on the y. There's no way to turn a 1 into a 2 while also turning a 3 into a 1. So those two are not parallel. A 1 and a 1 is good. It should mean these are the exact same. But of course a 3y and a 2y are not the same. So none of these normals are parallel with one another. Therefore, okay, so immediately, right, as soon as you see that, you've just cut your possibilities down from 8 to 3. Therefore, we have case 6, 7, or 8. Okay, those are the only things that could happen. Okay, I'll just do this a bit faster this time. Okay, so we are trying to tell the difference between one of these three. Now, what we're going to attempt to do is solve it. Okay, I mean, okay, again, in the benefit, so like, if you're doing this by hand, I would skip the coplanar step. If you're doing this with technology, right, or if you're doing this, let's say, to prove to me you really know your stuff, I don't know why you would need to do that, but let's just wink wink and say you might need to do that. You know, do the coplanar test. Right? Let's do the coplanar test and we'll check. Let's just change these so these are fine. And then x minus 2y plus 2z equals negative 4. Okay, so again, let's hide them so we don't know. So I think if I go normal, if I go perpendicular, no, okay, never mind. All right, so anyway, first normal is 1, 3, negative 1. Second normal is 2, 1, 1. Third normal is 1, negative 2, 2. Let's cross n1 with n2, and then let's dot that number with n3. It gives us 0. So again, this is a bit of overkill in my opinion if you're doing it by hand, but it's not. It's pretty quick to do on here. You're just typing it out. So what I'm going to do here is I'm going to go n3 dot n1 cross n2. Yikes. Was equal to 0. Okay. Therefore, case 8 is eliminated. You can't have case 8 if these are coplanar, right? So they're coplanar, so that's not an option. So what we're going to do is we're going to attempt to solve the system. So let's do the usual thing. Equation 1 and equation 2 would work nicely because I could just add them together to get rid of z. So let's say work with EQ1 and EQ2. So the first equation, x plus 3y take away z is negative 10. Okay. Second equation, 2x plus y plus z equals 8. Okay. Again, I can just add these together. It's pretty straightforward. 3x plus 4y, z and z eliminate, and then I get negative 2. Okay. So then I'm going to go work with, now let's see, which would be easier to eliminate z? It doesn't matter because they both have the same thing, so let's work with 2 and 3. Okay, so equation 2 we already have, 2x plus y plus z equals 8. Equation 3, x minus 2y plus 2z is negative 4. Okay, and just while I'm here, I'm going to put the color of this one in blue to remind us that that's one of the ones we're going to need later. Okay, so these two, let's say we double EQ2. So we get 4x plus 2y plus 2z equals 8. Underneath it, x minus 2y plus 2z equals negative 4. We'll subtract. 4x take away x is 3x. 2y take away negative 2y is positive 4y. And then we get 12. And this is going to be, use our two equations without z to keep going. This will be our orange equation. Okay, so we'll copy that down there, copy this underneath it, and if you look closely, what you're going to see here is that you can subtract right off the bat because they are parallel with one another. Anyone can explain to me how this program works? I will be forever in your debt. We get 0 plus 0 equals 14, and this is never true. Therefore, there is no intersection and no solution. So, therefore, we are looking at case 6, which is intersect in pairs. Now, let's draw it again. Let's have a look more closely. When you look at this from the correct angle, you realize that they kind of make an A shape, right? Like, and they're never going to get any closer, right? It's like a hole is in the middle of it. Maybe if I get rid of the axis here, it'll be easier to see. And let's get rid of these vectors. Okay, you see if I look at it just right, they form that sort of A shape, and they have that hole in the middle that's not getting It's not getting any closer or farther, right? It's sort of because the three normals are coplanar and they all exist on a common plane. So you're looking at case 6 and there's no intersection. So once again, if we go intersect EQ1 with EQ2 and then intersect EQ2 with EQ3 and then we type distance FG, we see that F and G, the closest they ever get together is 7.62, which means the solution to one set of planes and the solution to another set of planes never touch, and therefore there is no common solution that is common to all three of them, right? So you can see that the three, we could also intersect EQ1 with EQ3, and that would just give us that one there. Okay, so there you go. So that's that case is the case 6 where it's inconsistent because there's nowhere that's common to all three. So let's just write our answer down. We're looking at case 6, intersect in pairs, and there's no solution. Okay, last one's just kind of more of the same. So let's give this one a try. So it looks as though 1 and 2 are parallel, right? So if I go n1 times 2.5, I get times negative 2.5. I would get negative 10, positive 5. So negative 10, 5, and then 6 times 2.5 is 15, and it's negative. Okay, which is parallel to n2. Okay, now the third one, I don't believe would be parallel to any of them. Oh no, it would as well, sorry. N through n1 times 1.5 would give me 6, negative 3, 9, which is, you know, okay, so sorry. N1 back. N1 is parallel to N3. Okay, and the same thing would be true up here. I guess I'll just write this more technically. So we'll work on our form since we're at that point in the year. So N1 is parallel to N2 and also parallel to N3, so all three vectors are parallel. So therefore, since all three we have case 1, 2, or 3. Okay, so it has to be one of those original cases because those are the ones where everything was parallel. So let's just go back and copy paste that quickly. Now, this can be a bit tricky. I mean, it can be a bit tricky. Not really too bad because all you're trying to do is establish, are any of the planes coincident? Again, to do this, what you want to do is you want to try to solve. So let's say we worked with EQ1 and EQ2. So EQ1 is 4x minus 2y plus 6z is 35. And EQ2 was 10x minus 5y plus 15z equals 20. That should be minus 15z. And it should be positive there and negative there, right? Okay. Now if you try to solve this, so we'll multiply the EQ1 by 2.5 since we already did that. Sorry, by negative 2.5. Yeah, negative 10x plus 5y 5y minus 15z. At 2 point, I guess this was actually not such a smart idea. Okay, let's multiply the top one by 10, bottom one by 4. I don't want to work with decimals, don't ask me why. Okay, 40x minus 20y plus 60z equals 350. Underneath that, negative 40x plus 20y minus 60z equals 80. Now obviously when I add these together, I get 0 equals 430, which is therefore the system is inconsistent. Now, normally that would be enough to be done. But there are two inconsistent systems here. So that all this tells us is that case 3 is eliminated. It can't be case 3 because we just showed that the first plane and the second plane are distinct. So we might have this case where all of them are distinct, or we might have this one where two of them are on top of one another. Okay, so what we should do next is we should test EQ1 and EQ3. Okay, so let's try to solve. Okay, so again, 4x minus 2y plus 6z equals 35. Underneath that, 6x minus 3y plus 9z. Negative 50. Okay. Anyway, okay, so we'll go multiply EQ1 by 6, or by 3, and EQ2 by 2. Okay, so we multiply the top one by 3. 12x, take away 6y plus 18z equals 105. Bottom one, if we multiply by 2, 12x minus 6y plus 18z equals negative 100. We subtract them, we get 0 equals 205 again. So okay, so what we just did, we showed that pi 1 is not the same as pi 3, but there's still the possibility that pi 2 and pi 3 are the same. I mean, they're not because you can just kind of look at them, but let's just be thorough. Okay, so let's compare. So try to solve EQ2 and EQ3. Okay, so EQ3 was 6x. We'll do it in order. 3y plus 9z, negative 50. That was EQ3. EQ2 was negative 10x plus 5y minus 15z equals 20. Again, rather than multiply this time, let's divide EQ2 by 5 and EQ3 by 3. Okay, so we divide the top one by 5. You get negative 2x plus y minus 3z equals 4. Divide the second one by 3, you get 2x, minus y plus 3z equals negative 50 over 3. And then what we can do is add, and we get 0 equals, negative 38 over 3. Which again is false. So pi 2 is not coincident with pi 3. So therefore, we have case 1 where all three planes are parallel and distinct. Okay, and just to understand, there are 0 solutions. Okay, last thing we're going to do today is just quickly draw this so you can get a look at it. So let's change equation 1. 4x minus 2y plus 6z equals 35. Equation 2. Negative 10x plus 5y minus 15z equals 20. And you can see it's kind of reducing them for us. 6x minus 3y plus 9z equals negative 50. And there you go. 3 planes, all parallel, all distinct. Okay, so just one thing I think would really show that you know how to do this besides doing my assignment, the final assignment is quite difficult. Make sure you can do that one. If you really want to show that you can do this, you might design a question. And, I don't think I would worry too much about, cases 1 through 5. Because honestly, cases 1 through 5, these are not that difficult. But if you could design a problem and then show how to solve it for each of these and how they're different and why they're different, that would really demonstrate that you have mastered this content. So, use GeoGebra. It's your friend with this, right? You can it's very good with these planes and intersecting them and everything you need. So, use it, experiment, try to figure out how to create a question that's going to end up like this versus one that's going to end up like this versus one that's going to end up like this. If you could show the steps to construct an equation, that would go a long way to showing that this material, right? And obviously how to solve it. We're always kind of solving it the same way. I am going to do another lesson. It's optional, but I just want to announce it now, where we're going to talk about this last piece. There's a few things here that make what we're doing today a little cleaner and easier to do. But anyway, that's it for the course. So you've completed the content. So try your assignments and make sure you post your questions.